Welcome, curious minds, to Factopedia, the podcast that dives headfirst into the fascinating world of, well, just about everything. Ever wondered why the sky is blue, or perhaps the secret ingredient in your favorite painting? Maybe you've pondered the science of a good laugh, or the surprisingly dramatic history of something utterly mundane. Here at Factopedia, we believe that the universe is brimming with incredible stories, hidden in plain sight. From the smallest atom to the grandest empire, from the deepest emotion to the silliest trivia, we're here to unearth the most interesting, mind-blowing, and sometimes just plain bizarre facts out there. So, buckle up and get ready to have your knowledge expanded, your curiosity piqued, and maybe even your socks knocked off. This is Factopedia, where we dig deeper into the facts that make our world, and beyond, so wonderfully weird and wonderful. Let's get started.
From the first crude carts to the Mars rovers of today, the wheel has been a cornerstone of human progress. This simple invention has revolutionized transport, trade, and even our understanding of the cosmos. But what if I told you this seemingly simple invention hides a fascinating paradox? In ancient Greece, a perplexing problem emerged. Known as Aristotle's wheel paradox, it challenged the foundations of geometry and motion. How can two concentric circles traverse the same distance in the same time? A simple question with profound implications. Imagine a car tire rolling along a road. Both the tire and the hubcap complete one full rotation. Yet the tire travels a longer distance. How can this be possible? This is Aristotle's wheel paradox. Join me as we explore this ancient paradox. We'll trace its evolution through history, from antiquity to the Renaissance and beyond. Prepare to delve into the fascinating world of geometry and motion. Let's dive deeper into the heart of this geometrical puzzle. Imagine two concentric circles, one inside the other, sharing the same center point. Let's call the bigger circle big, and the smaller one small. Now imagine these circles are not just abstract shapes on a papyrus scroll, but rather the two edges of a chariot wheel rolling across the ancient Grecian landscape. As the chariot moves, both circles, big and small, complete one full rotation. They start together and finish together. Here's the catch. The circumference of big, the outer circle, is undeniably longer than the circumference of small, the inner circle. Basic geometry tells us that. So, if they both start and finish their rotations simultaneously, wouldn't that mean big traveled a longer distance in the same amount of time? This seemingly straightforward observation leads us to a perplexing conclusion. Either our understanding of circles and their properties is flawed, or our perception of motion itself is misleading. This is the crux of Aristotle's wheel paradox. It throws a wrench into our intuitive grasp of distance, time, and the relationship between a circle's circumference and its rotation. The enigma of Aristotle's wheel paradox didn't fade with the passing of ancient Greece. Like a mathematical torch passed down through generations, this problem captivated thinkers throughout history. From the mathematicians of the Islamic Golden Age to the scientific revolutionaries of Renaissance Europe, each era grappled with this geometrical puzzle, adding their own insights to the ongoing debate. Girolamo Cardano, the 16th century Italian polymath, known for his work in algebra and probability, took a swing at the paradox. He suggested that perhaps the smaller circle, while appearing to move in sync with the larger one, was actually experiencing a series of microscopic jumps or slips. These imperceptible discontinuities, he argued, could account for the difference in distance travel. Then came Mersenne, a French polymath, who approached the paradox from a different angle. He proposed that the true measure of motion shouldn't be based solely on the distance covered, but rather on the quantity of motion involved. This concept, a precursor to the modern idea of momentum, attempted to reconcile the apparent discrepancy in distance by considering the force and resistance at play. Section 4. Unraveling the paradox. A matter of perspective. Galileo, father of modern science, entered the fray with his characteristic ingenuity. He dissected the paradox by imagining the wheel not as a continuous object, but as a collection of an infinite number of infinitesimally small lines. Conceptual leap allowed him to break down the problem and analyze the motion of each tiny segment individually. Bolzano, a 19th century mathematician and philosopher, offered a more abstract interpretation. The paradox arises from our flawed understanding of infinity. The concept of an infinite number of points on a circle, he suggested, is paradoxical in itself. We cannot apply our finite reasoning to grasp infinite. The paradox, even today, remains a source of debate. Some mathematicians argue that the smaller circle isn't truly rolling in the same way as the larger one. They propose that it's actually experiencing and slippage, which accounts for the difference in distance. Section 5, The Wheel's Legacy, From Ancient Riddle to Modern Marvel. While a definitive, universally accepted solution to Aristotle's wheel paradox remains elusive, the journey to unravel its secrets has been anything but futile. This ancient riddle has forced us to confront the limitations of our intuition, challenging our understanding of geometry, motion, and even the very nature of infinity. The paradox highlights the importance of perspective in scientific inquiry. What seems like an insurmountable problem from one vantage point might appear perfectly solvable from another. It underscores the power of abstract thinking, encouraging us to go beyond the limitations of our senses and explore the universe with the tools of logic and mathematics.